four we still need to cover. Now, you guys were great about telling me about an atom. So, what's the center of an atom we call the nucleus. So what's in the nucleus?
Protons and neutrons.
Protons and neutrons. Perfect. Let's see. A little bit of board down here. So protons and neutrons, and here's the deal. We can count protons and neutrons, and we come up with what's called the mass number. So here's my nucleus. Here's my plus for a proton. Here's my 0 for a neutron. And we talked the other day that because this has 2 protons, I know, if I had a periodic table in here, I know that with 2 protons, it's got to be a helium atom. So the protons say what sort of element it is. The other thing is, I mentioned mass number. If you can look, and this is my cloud of electrons, if it's neutral, how many electrons does it have? If I have 2 protons, how many electrons do I have? I have 2 electrons. Yep, I'll just put an E with a little superscript negative. There's my helium atom. Now, mass number is we count mass number. We count number of protons plus number of neutrons. So what's the mass number for this atom?
4.
4, exactly. Here's the deal. The protons set what element it is. And I kind of talk about neutrons as if they're kind of like the spice of life. Neutrons can vary. So because they can vary, we can get different mass numbers for the same element. Does that make sense? Actually, that brings us to this idea of isotopes. Isotopes just means that the number of neutrons are just kind of a little bit different in an atom with the same number of protons. So they're way different. So here I have some examples down here. The symbol C, of course, C stands for Of course, C stands for carbon. Here we have a carbon mass number 12, carbon mass number 6, carbon mass number 14. Looking here, can you see how many protons, it's on the slide, how many protons do each of those isotopic forms of carbon have?
They all have 6.
They all have 6. So if that's the case, how many neutrons does this with a mass number of 12 have? 6. And he got that by taking 12 minus 6. For carbon 13, how many neutrons?
7.
7. For carbon 14?
8.
8. You guys ever heard of carbon 14 dating?
Yeah.
So what that does is it just makes use of this special type of carbon. I'll leave it that way. Okay. What else we got? I think that's about it. The big thing here, and I was looking for like little labs for us to do, and there's one that I doubt if we'll do, but we might. Basically, you take marshmallows and you pretend like they're protons, and then like for instance in the sun, one proton, which is hydrogen, and one proton, which is another hydrogen, come together, and it's a little more complicated than this. They squish together and they make 2 protons, which is helium. But the whole marshmallow thing kind of catches my eye. So, most of the universe still today, if we're going to step outside of our Earth, step outside of our system of planets in the sun, we're going to step outside of our galaxy. If we were to take a bird's eye view of the universe, most atoms out there are hydrogen. They still are. Okay, and if we look around and like, dude, there's a lot more than hydrogen is what I'm looking at. So, yes, sir.
So there's a lot of hydrogen and oxygen and stuff out there. Why can't we breathe in space?
Oh, outer space is mostly a vacuum. Outer space is like got nothing. Got nothing. It's the gravity of a planet that helps it have gases in it. We'll call an atmosphere. So yeah, that's true. Yep. And the thing about the planets is like if you were to go to Mars, its atmosphere isn't nitrogen and oxygen. The Martian atmosphere, maybe if you watch the movie The Martian, it's carbon dioxide, mostly carbon dioxide. It's thinner.
Is that on Mars?
Mars, yeah. So each of the planets has kind of a different gas it's got. Which actually brings me up to this idea. Carbon dioxide, what's the formula for carbon dioxide?
CO2.
CO2, carbon dioxide. So the thing about that is we know that in order to make that molecule, that unit, CO2, we need one carbon atom and two oxygen atoms. What's the formula for water?
H2O.
Yep, H2O. Okay, two hydrogens and one oxygen stuck together. So these are actually examples of molecules, and they actually were built from atoms. And the reason they stick together is, we get into that more with chemistry, it has to do with the electrons. Yeah, we use formulas to represent compounds. Do you think that there's compounds in outer space? Yeah, that's true. Not in outer space, because it's hard to get an atom, even. Outer space is very sparse. But where you have atoms kind of joined together with a certain amount of density, then you can start to get molecules. Exactly. Well, yeah. In fact, in order to kind of look at where new things might be formed, new stars, we look for these clouds that have carbon monoxide. What's the formula for carbon monoxide?
You said carbon what?
Monoxide. Monoxide.
CO.
CO.
Because mono is.
Yep, mono is one. You got it. Now switching gears a little bit, and you talk about energy. We see energy all the time. We just, I think, kind of take it for granted. We expend energy as we walk. If you can see anything, it has to do with light energy. You got here in a car that used energy. And basically what your car did was it runs on gasoline. So as the gasoline's sitting in your tank, we call that potential energy. Potential energy means it's stored energy. It's just sitting there. If I had a battery here, if I pop the batteries out of this, that would be stored energy in my battery. But as I use this to make a light like that, kinetic energy, yeah, energy being used. Okay.
In science, they used to compare like a car sitting on the hill is potential, and then one that's rolling down the hill is kinetic.
Yeah. Yeah, if it's sitting up on top of the hill, not doing anything, it's potential, it's stored. And if it's got the ability, especially to go downhill as it's moving, that's kinetic energy, exactly. So another type of actually kinetic energy is energy associated with motion. And I'm going to try to convince you that when you take a thermometer, if this is my thermometer, and if I dip my thermometer in a chunk of gas or liquid or solid, or just in this air, my thermometer is measuring the kinetic energy of the stuff it's in contact with. So what happens, like if I take a thing of water, just liquid water, and I'm bringing it today, but if I take a thing of liquid water and heat it up, what happens to the water molecules? Do they go faster or slower?
Faster.
They go faster, yeah. And if I have a thermometer in there, what does my thermometer indicate?
The temperature of the water, right?
Yep, temperature of the water goes up, yep. So that's kind of how that whole thing works.
If it's a solid, they barely move. If it's a liquid, then they move faster, and if it's a gas.
Exactly, yeah, exactly. Solid, you might look at this like, nah, those particles aren't moving. But honestly, the molecules and the atoms that make up the molecules, probably some sort of plastic, right? Not real wood. Actually, there is motion. There's just not as much. Could we liquefy this desk?
Yes. With enough heat.
Could we gasify the desk?
With enough heat.
Yeah, with enough heat, yeah. One of my things I talk about in chemistry is like, if on Thanksgiving morning, if you can smell your turkey, okay, basically you are getting gasified turkey molecules. It's like turkey vapor. Think about it. Sorry.
It's like when you start smelling coffee.
What's that?
I said I can't do coffee, but everyone's like, "Do you smell coffee?"
I know, I like the smell of coffee. Yeah, if I can't drink it, if I can smell it, that's like second best. But you don't like coffee, oh, that's bad. Sorry.
Yeah.
I don't like coffee either. It's not obvious to me.
So this last example, so over here, you guys told me that if I heat it up, it goes faster. So kind of from left to right, can you see where here the lines are longer? Okay, so that just means indicating faster, slower. This is the colder temperature, this is the warmer temperature. Now over here, we've got two things. They're both at, well, I guess one's at 100 degrees Celsius and one's at 200 degrees Celsius. What temperature does water boil at in the Celsius scale? Water will boil at 100 degrees Celsius. So at 200 degrees Celsius, you're looking at water that's not liquid, it's a gas, right? So here's the deal, and we kind of have to quantify this when we talk about temperature. If we want to translate it to energy content, thermal energy content, we have to talk about how fast the particles are going, how much kinetic energy they have, and then actually kind of how much mass or how much density they are. Okay, so this is to say, even at this lower temperature, and I don't have the math here to do it, yeah. This is a lower temperature, right? Water boiling at 100 is lower temperature than the gas. But this pot of boiling water, oh man, so it's got more thermal energy because of the mass it's got there, even though it's a lower temperature. Okay, it's a lower temperature, but it's not just temperature, it's how much thermal energy something has. It's also the mass. Okay, so temperature scales. So if you're like me, you're all about Fahrenheit. Like, it's supposed to be like, it was 69 this morning when we walked our dogs. It's going to be 71 is the high today. Fahrenheit, okay? If you were in England, you'd be talking about Celsius, okay? So we're all about Fahrenheit. Celsius is metric. Also metric is the Kelvin scale. So if you're not familiar with it, I'm going to throw one more temperature scale out there at you. It's also Celsius. And we've got the 3 temperature scales. Here's Fahrenheit. Okay, here's Celsius. We said that water boils at 100 degrees Celsius. On the Fahrenheit scale, it's 212. Okay, now the Celsius, which is metric, and the Kelvin, which is metric, are linked. And here's how they're linked. 1 step on the Celsius scale is equal to 1 step on the Kelvin scale. They're just offset by 273.15. So here we go. If we're going to go ahead, notice that 100 degrees Celsius is 373.15 Kelvin. Let's go ahead and back that down 100 degrees. 0 Celsius is 273.15 Kelvin. Let's back that down 273.15 units, and we get to this important thing called 0K, or 0 Kelvin. And some of you guys may call that absolute zero. So this is absolute zero. So we said that all matter has kinetic energy, all matter has motion, and the solids have less motion, the liquids have more motion, and the gases have got it all. They have all this terrible, crazy motion. Okay, but even gas particles, if you lower their temperature, will go slower and slower and slower. So like the slide says, if you lower the temperature of a gas to 0K, its motion stops. And then you kind of hit something, you're like, okay, so all atoms have motion, but that atoms at 0 Kelvin have no motion. So did that just violate what you said? And the answer is yes. So 0 Kelvin, all motion stops. Motion of atoms, motion of molecules. And 0 Kelvin is not been achieved. Really, actually several years ago, there was an article that came out and they had like negative Kelvin units. I'm like, wow, that's pretty cool. And what it was they kind of did a little bit with statistics and kind of a bell curve, so some of them fell on, so no, it was not negative Kelvin. Pluto is about 5 Kelvin. Pluto actually has some zones. It's like 5, 11, yeah. So it's pretty darn cold. So yeah, let's talk about that whole potential energy, kinetic energy. So potential, think it has the potential, we call that stored energy. Kinetic energy is energy associated with motion. So if we were to throw this ball up, it would only go so far, and if we were to kind of be able to take a snapshot, when it got the highest, how fast would it be going? 0. Yeah, when it gets its highest, it's going 0. So if something goes 0, how much kinetic energy does it have?
No, it's stored.
None.
So it's
Exactly. So here it has 0 kinetic energy, but it has the potential to fall all this way, is the way I think of it. So it has the most potential energy, 0 kinetic energy. What about right before it splats?
That's the most it can possibly achieve.
It has the most speed it's gonna have. With speed or velocity, it's got the most kinetic energy it's gotta have, but it's got the potential energy of basically nothing. So this would have the lowest potential energy and the highest kinetic energy. So I think that's what this slide says. So this one is high KE, low PE, and this one you guys told me is going to 0, velocity 0, so it's got a low kinetic energy and it's got a high potential energy. Well, one more thing with regard to potential and kinetic energy, and this actually has more now to do with kind of the formation of suns, the formation of stars. Well, I guess we only have one sun. Formation of stars, the formation of planets. When we talk about the formation of our sun, I think we might have touched on it already. We're going to say it started back in this big cloud. This big cloud. So this cloud, it could be that cloud right there. Okay, ultimately, the atoms came together and formed our sun and our planets. So here's the deal with regard to potential energy and kinetic energy. Something that's spread out like that, like you see that cloud, has a lot of potential energy. And as that thing shrinks down, it has less potential energy. Now, if something loses potential energy, it must gain kinetic energy, just like we saw a minute ago. So this one has high potential energy, high PE, and this one has low potential energy. Just like we saw before, what's that mean? That means that this has low kinetic energy and this has high kinetic energy. So one of the things about kinetic energy we talked about is kinetic energy is associated with motion, and motion actually, if you have a thermometer, can be shown to make your thermometer go up. So here we basically have kind of a look behind the scenes at what's going on with basically a cloud, we're going to call our solar nebula, forming the sun and the planets. So this is a mushroom cloud, okay, and in a bomb like this, in a nuclear bomb like this. This is right. This is right. Well, let's call it the hydrogen bomb, the H bomb. Okay, in a nuclear bomb like this, it's set up to take hydrogen, and it's a hydrogen bomb. Take hydrogen plus hydrogen, fuse them together. What did I say you get after you take hydrogen plus hydrogen? You get helium, and release a lot of energy. And I think I showed this the other day. This is Einstein relating how much energy is released, okay, by taking some mass. The thing about it is if you weigh the two hydrogens and if you weigh the helium you form, the helium you form is lighter. So that mass that went away is converted to energy. So anyway, that's what our sun's doing. So I finish up with this, and actually this slide, clear at the end of the semester, we talk about kind of how not our solar system, but how our universe unfolded and created the fabric of space and time and all that. We had to create these 4 forces, we call them fundamental forces, that are still here today. So gravity, the force of gravity, and I'm not going to say that scientists know all there is to know about gravity, because they don't, but it's a fundamental important force. They can measure it, say a lot of things about it, how it behaves, okay? Electromagnetism, that's basically where your pluses and your minus want to attract. We have electromagnetism going on within an atom. Here's my helium atom here, okay? Because we have positively charged protons, negatively charged electrons. And then we have things that are associated with the atom on a very small scale. Okay, so these are going to be due when we meet again on Monday. Thank you. These are due Monday. So part 4 due Monday. And let's take a look at part 8. What's that?
Is it 8A or 8C?
This is 8A. Yeah, I'll try to go in order next time. I don't want to, but I'll try to. If I just make the labs a little out of order and just keep the regular order in lecture, I'll try that. Okay. So, asteroids. What's the difference between an asteroid and a comet?
Comets are like really fast, and asteroids just kind of float.
Oh, I could see that. What else? Like in lab, what was the lab that we did a little bit ago?
Comets are like really cold.
Comets are really cold. Yeah.
Burn up when they go around the sun.
And they leave a trail and kind of disintegrate as they go around the sun. Exactly. Now, with that said, I don't mean to throw you off. This actually, I want to talk about asteroids and stuff. This is not an asteroid. This is a comet. Okay. Two tails we talked about with the comets. What direction did the tail point? Do the tails point? Away from the sun. Yep. Comet tails will generally point away from the sun. Starts letter N. What do we call that thing that's right here? The rocky part for a comet. Remember?
The tail.
Yeah, these are the tail. Nucleus.
Oh,
very good.
I'm thinking. Okay,
Yeah, and the coma around it.
Not bad.
But I want to switch gears a little bit to asteroids. And yeah, the asteroids are not cold. And they're not cold because of kind of where they're formed. They're closer to the sun. Asteroids are closer to the sun. So this one should go pretty fast because I have a lot of just kind of pretty pictures. Asteroids, I think I mentioned the other day, are in the news for let's go out and get those minerals, okay, in the asteroids. Oh, no, it's an interesting idea. Yeah, who's got rights to that? Oh.
First person that gets there, go.
And first person that gets there, go. And honestly, we have scientists have studied asteroids. In part because they want to know a bit about them in case we have to defend ourselves from them. So yeah, asteroids look kind of different. Now, there are some kind of spherical asteroids. You kind of see these up here. Some asteroids, just a few asteroids have cool names. We have a couple cool named asteroids. What do we call that? After Mars and before Jupiter, we call that the asteroid belt, exactly. This guy Vesta, or this gal Vesta, is in the one of the two large asteroids in the asteroid belt. The larger something is, it kind of becomes spherical. So you can kind of see it's spherical there. But this says if you were to take the crumblies between Mars and Jupiter and try to make another planet, it would not be large enough to be a planet. Now, the only way we see asteroids is the same way we see the moon. How can we see the moon? Does it glow on its own?
No.
No. So we see it because
they're hit by the sun.
Yeah, it's hit by the sun, exactly. So this right here is actually, and we've talked about star trails in here. This would be like a star trail, but over the course of a night, and you can see this motion here is an asteroid moving. So basically the light is shining on the asteroid from the sun, and we're seeing that sunlight bounce off the asteroid, and the asteroid's moving. I think that's kind of cool. And I'm not sure how they knew. That little asteroid Vesta in the asteroid belt, here's a piece of Vesta. When I think of things like this, so this landed on the Earth. When I think of things like this, I think of, oh my gosh, our solar system, which now has the sun and the planets orbiting around it, used to be a crazy, really bombarding place. You can see that when you look at the moon with all the craters on the moon, and you see when you see this. Here's some more asteroids: Matilda, Gaspra, Ida.
Little grass there, he's so small.
What's that?
I said poor little grass there. So
Gaspra, yeah, he's so small. Hey, but can you see like the little crater, the cute little pock marks on these asteroids? I think that's kind of fun. Now, the fact they're not spherical just means there wasn't enough mass to kind of take the rough edges off. I mentioned they've been visited. These actually were visited by a spacecraft near Shoemaker. This is kind of interesting. Can you guys see this one right here? This is an asteroid that has its own moon. Why not? Yeah. that not adorable? Just a whole gravity thing. Kind of random. When we study Mars, we're going to see that Mars actually has moons, but they were captured moons. So Mars has moons that look like a potato, kind of like this. Not our beautiful moon. Eros. Itokawa. This caption actually says, now, do you see where this looks like a little bit rough? One thing about asteroids is some of them they think was like, it's like Frankenstein. It's got like these loose, gravel, almost look gravelly pieces that gravity is just kind of tentatively having it stick together. So with that sort of asteroid, if it was headed towards us, it might be a candidate to, I don't know, blow it up. As long as its little pieces were small enough then not to cause harm when they fell through the Earth's atmosphere. I don't know. All right, so here we have Vesta, and this is Sirius. So I said Vesta was in the asteroid belt. You can kind of see it must be pretty big because it's spherical. Sirius is also in the asteroid belt. Sirius is so large, though, that it's categorized as a dwarf planet. What else do you know is categorized as a dwarf planet? Pluto. So this would be, Sirius would be Pluto's cousin. So they've gotten some great spacecraft, I'm not sure which one, but they've got some great images of Sirius. And see that white little thing? I mean, to be a scientist, you know, and to be seeing this firsthand would be just amazing. Like, what the heck, right? So I'm going to see that kind of close up here. What's that?
It has a pole.
Yeah, I think so. So here, in fact, it has a pole would mean it's kind of rotating on an axis. But that's the bright spot. Salt deposits. Aliens. Well, salt deposits, so why not go ahead and sit there and mine it? But, so I need to talk about, and if you're kind of following along in the notes that I printed out, I just this morning changed the title of this slide. So instead of saying asteroid belt, now it says various asteroids. So there's 3 types of asteroids you're going to need to know and where they're located. So right off the bat, most people know the ones that are between Mars and Jupiter in the asteroid belt. We don't care about those because they're not going to hit us. This next kind won't hit us either. They're called, I usually call them Trojan asteroids, but here they call them Trojan and Greek. So this orange line here is Jupiter. Big brother Jupiter, and there's these stable regions ahead of Jupiter and stable regions behind Jupiter as it orbits with a cute little cluster, almost like gnats, that kind of escort Jupiter around. So the Trojan and the Greek asteroids actually are a little in front, a little behind. And if you're into math and all that, math, of course, and science intersect quite nicely, and it's like a mathematical sweet point called Lagrange points. We actually, Earth has kind of a set of escort asteroids around too. But anyway, the last one, that's what you got to worry about. Apollo asteroids. They are your wild childs. Now, it's possible to take I think this would be possible. It's possible to go ahead and take a Trojan or a Greek asteroid and have it kind of nudged and to become a wild child. Apollo asteroids are random. Okay, they orbit the sun, and as they're random and orbit the sun, they can cross Earth's orbit. So that's the scary ones. This is actually just kind of showing you that Jupiter still does some funky things with the asteroids in our asteroid belt. But the presence of Jupiter probably kind of stirred up those belt asteroids so they couldn't form another planet. All right, what else do we got? So this is a look at the little dots are asteroids. You see the belt asteroids, you see the Trojan, the Greek asteroids. All right, one other thing, or another thing I need you to know in this class is there are 3 M's, okay? There are asteroids, well that's not an M, but asteroids and meteoroids. Can you hear the roids in it? Hemorrhoids, no. Asteroids and meteoroids, okay? Meteoroids are just smaller asteroids, quite honestly. So asteroids are like space rocks, just out there minding their own business, and so are meteoroids. Now, meteors then are momentary. Meteors are the streak that's created as the material vaporizes, mostly vaporizes in Earth's atmosphere. So meteors are momentary. The third M is a meteorite. And actually, as I got back from summer break, I'll pass this around. Not mine now. As I got back from summer break, one of our maintenance guys had this on my desk, and he's like, "Hey, Libby, is this meteorites?" So meteorites are basically stuff, and it happens, that didn't get burned up in the atmosphere as it fell through, creating that streak. So it's a meteoroid that created a meteor, and something's left over. That's a meteorite. What's that?
Superpowers.
Okay, you got superpowers? Okay, here's a picture of a meteorite here. Okay. Now, I don't know how this works because I'm not familiar with the whole radioactive and all that, but I'd be kind of a little bit afraid of sometimes radioactivity after it's just freshly fallen. So there's two types of rocks that you can pick up. There's the primitive ones that would be old timers in the process that have kind of been around or kicked around a while in outer space. That streak there, so what's that streak called? Is it a meteoroid, meteor, or meteorite?
Meteor.
It is a meteor. Yep, the streak is a meteor. And you kind of see some color here. So if you do a shower for your labs, meteor shower for your lab, which is exciting, kind of you'll sometimes be able to see colors, sometimes not. Kind of got some greens and some yellows. See what I mean about the whole, are you really going to put your kid on that space rock? Superpowers. Naya, what? These little kids, I want to track them down. So there's a big old meteorite.
One of them's Clark.
This actually is a good thing to kind of get in your mind and emphasize that a good place to pick up meteorites is on fresh snow. Here's a meteorite that went through this car. And here's 3 types of meteorites. So I don't know, to me, when you look at that, and if that is a meteorite, people, y'all just touched like, I don't know, $100,000 or something right there. So I should be locking up my office. Okay. So anyway, where did you find this? One of the maintenance guys wants me to see what I can track down about it. He got from his dad. That's what I asked him. Oh. So I don't know. It feels like pretty irony, pretty dense.
Pretty sure you should split that 50-50 with me.
I don't know.
Whatever it's worth.
Right?
50-50.
But that's all I got for 8A. And so we still just have 8C, okay, on Monday. And I didn't hand back your, remember the other day you guys watched the video and you came up with some questions? You'll notice that at the end there, I'm so excited, if you flip over my review sheet, you should see one of your questions there. So anyway, it's fun. Okay, have a great weekend. Go out and see the moon on Saturday. And knock out a lab if you want.
So do you just have
I
questions?
asked all my questions and we just do the homework because I didn't mark down this. That's really what you needed.
Yeah.
I couldn't find it on Canvas. I was getting confused.
Yeah.
It's out of order, so that's why I'm like, we can't be on Canvas already. So
Okay,
I got
very
it.
good.
Thank you.
Yay, thanks.
Corey, give us my pencil.